Hello everyone. Welcome to the presentation on AC and DC arc flash methods for renewable energy systems. I'm your host, Raghu Veera Raghavan, and I worked on the engineering services for this project with Gabriel Molina from Blue Oak Energy LLC. On behalf of ETAP, we thank Gabriel for giving us the green light to share the experience and lessons learned in this project while performing arc flash analysis. Due to some emergency situations, he was unable to share it himself. This project consists of addition of renewable energy sources to an existing facility, and which included 63 PV arrays and inverter units associated with them. Each PV array is rated up to 2.8 megawatts. And this was served by a 34.5 kV substation unit with normal and standby power sources. The required studies within the scope of the project was to perform short circuit analysis for maximum and minimum short circuit currents, protection and coordination settings review, where we tried to evaluate the current protection and coordination settings that was already given to us, and to perform arc flash analysis on the low voltage equipment on the inverter side, and then the worst case incident energy analysis on the medium voltage equipment on the 34.5 kV substation side. In addition, we also performed the arc flash analysis for DC PV disconnects approximately at 1500 volts DC. The model creation was based on submittal data and initial ETAP project with the client data, and this included the medium voltage switchgear details and the inverter modeling, along with the initial arc flash input parameters that was provided by the client, and the protective device settings and the corresponding relay wiring diagrams were also given to the model from based on the manufacturer data and other protective devices in the field. The AC short circuit analysis included both maximum and minimum short circuit calculations, and we had several switching configurations representing the PV arrays on and off conditions using ETAP, and all equipments were found to have satisfactory interrupting ratings. So the maximum and the minimum short circuit current on the PV arrays on the inverter side and also on the short circuit study on the 34.5 kV side was all satisfactory based on the initial evaluation done by ETAP, and the corresponding results were also added and documented as reports. The protection and coordination studies were pretty straightforward. The selectivity was much established, and they were having the fuse disconnects on the medium voltage side of the transformer, and which were rated correctly according to the NEC guidelines, and also based on the coordination settings with the upstream protective relays that are fed from the substation level. So the main challenge started from the arc flash low voltage equipment, which is basically on the transformer on the inverter side, and the incident energy analysis was done based on the IEEE 1584-2018 standard. The project was given to us with existing incident energy levels that give you an incident energy value of about 40 cals per centimeter square, and there was no PP settings available. And the incident energy evaluation on the inverter panels on the AC side seemed to be very higher at this location of the study. The original setting that was provided to us had a PV array fed by an inverter to an actual low voltage bus on the transformer secondary, and then it got stepped up to this transformer primary on the medium voltage side, and the initial incident energy based on the fuse clearing time was more than 40 calories per centimeter square with a high clearing and longer clearing times. At this point of time, I would like to show the ETAP model and explain how this particular setting was originally given to us and what are all the steps that was taken by ETAP to resolve this condition and evaluate the incident energy as per the equipment ratings and the data provided by the manufacturer. So based on the initial ETAP model that was provided to us with the corresponding settings of the protective device, we did have the substation feeding into all these 34.5 kV switch gears, and then they were all backed up by these inverter terminals that is fed from the PV arrays that contribute to the medium voltage side and the low voltage side respectively. and the corresponding PV on and off and the normal generator settings for the normal and standby sources were already achieved to us, which is this, out of the scope of the study. However, we did evaluate the incident energy based on the original setting that we had that would just give you the value about 40 calories per centimeter square. As per the project settings, we had the 1584-2018 method selected with the arc current variation applied. Although the protection seems to be pretty solid with respect to the short circuit current, the nonlinearity of the arcing current that caused a reduction in the arc current changed the entire trip time of that particular fuse that caused into a very high incident energy. So the original setting that was given to us based on the calculation that is performed started with a higher clearing time on the low voltage circuit breaker that is fed from the inverter. So upon further investigation, we did find out that the inverters have the capability to shut off based on the voltage write-through capability and to shut off based on the terminal voltage of the inverter fed, which was assumed to be 50%, and the trip time of 0.166 seconds. So we ended up with the inverters based on the manufacturer data that is provided to us. We enabled the auto trip feature that was given to us, and then we had actually selected the voltage at the threshold that is below the 50% of the inverter terminal voltage, which was actually determined by the short circuit study in ETAP. And upon selecting that equipment, showing that the inverter would shut off below the actual threshold voltage, the incident energy was reduced from very high large number to 62 calories per centimeter square. However, this was still over 40 calories per centimeter square, and this is because the fuse clearing time was at 0.79 seconds based on the current seen by the protective device, the fuse in this case, which was around 500 amps arc current. So as per the fuse device ratings and the corresponding transformer FLA, obviously the facility would not have a replacement in the fuse. We did provide some suggestions with actual mitigation techniques that would be based on working distance. So in order to make sure the actual working distance is varied, or to as a solution for mitigating the incident energy, we used our tools in ETAP to predict or to explain the client on how much the incident energy would differ based on the working distance mitigation technique. In order to evaluate different what-if scenario tools without running ETAP every time, we made use of the ArcFlash Power Calculator tool that is available in the ArcFlash page of the bus editor. And then the effect of the incident energy based on the arc current variation was actually determined how the values have changed from a very drastically large value after the inverter settings has been added to the auto trip feature. So based on this particular evaluation, at 100% arcing current, which is at 35.257 kiloamps, because the fuse having a very high inverse characteristics, we had the 100% arcing current, the minimum arcing current, which resulted at this clearing time of the fuse that would possibly give you the total clearing time and the corresponding incident energy over there. From the ArcFlash calculator, we are able to show the star view, and from the ArcFlash analysis point of view, that the 100% arcing current resulted at this particular clearing time, and then the reduced arcing current, which is the 538 amps seen by the fuse, resulted in the larger clearing time that would cause the incident energy to be 62.75 calories per centimeter square. So we used our ArcFlash tool calculator, power tool calculator, and we are able to get a trend given the fact that the fuses cannot be replaced because of the cost and the budget of the project. The another next mitigation technique to keep the existing system conditions is to use the incident energy evaluation based on a different working distance. So that is when we have the plot view feature in ETAP, where we are able to specify, okay, let's say we use the 1584 working distance values, typically starting from 18 inches, and try to see if we could increase the incident energy or decrease it based on the increase in the working distance, we were able to get a spectrum of plots that could be used for the same clearing time, because this being the longest clearing time that causes the severe incident energy, which we kept it at 0.791 seconds. And we were able to create a plot view for this, and that would basically give us the whole spectrum of how the incident energy could be mitigated, that we can add it to our analysis report or our findings report to the client. So we started at this level at 18 inches, and then this tooltip will provide you that, okay, approximately at 36 inches, I would have an incident energy way less than 40 calories per centimeter square. So the bottom line is the use of the calculator along with the protection and the coordination settings for arc flash, the results of incident energy could be easily evaluated without rerunning the study in ETAP for all the different facilities or all the different faulted locations per se. So this plot was one of the features that we have in ETAP that was helpful to determine the actual incident energy mitigation technique. Or in other hand, it is also be used to use the time slider option here to check the incident energy, how it could change based on increasing the working distance value. Switching back to the presentation, I could say here the ASPHONE settings without the auto trip feature enabled in ETAP, the incident energy was really high and unrealistic. And even the 2-second rule would still not give you the ballpark of 40 calories per centimeter square. So using the auto trip, we were able to make sure the fuse would clear the fault at this particular current level seen by the fuse on the arcing current point of view. And at the same time, the inverter would shut off itself because of its terminal voltage being less than 50% of the actual nominal voltage of the connecting switchgear. And based on the actual mitigation technique, we were able to say, okay, now that changing the fuse for the entire facility for all these PV array locations is going to be out of question, the next best bet or the next line of defense is to mitigate the incident energy through working distance, which could cause a much greater improved results and to achieve the goal for less than 40 cals per centimeter square. That was documented and given as a feedback to the client based on this analysis done by ETAP. On the other hand, the arc flash results for the 34.5 kV substation was also evaluated. And in this case, the client requested to perform the analysis using the IEEE 1584-2018 method, which reverts to Lee method, which is officially removed from the standard. So in this case, all the corresponding incident energy calculations at that location was already above 40 calories per centimeter square. So ETAP recommended the methods that is best fit for this particular application as the 1584-2018 standard, and its scope ends at 15 kV. So we had the EPRI method, and that was suggested for this particular application, and that would cause a much better improved results that we could actually evaluate between the location that we are targeting that is way above 40 calories per centimeter square. So we identified the worst case arc flash location from the arc flash analyzer based on the existing methodology used previously. We found out the Lee method was giving us a very high incident energy results for the given settings of the actual arc flash clearing time. So that is the reason why in ETAP we do have this calculation warning message that the theoretically derived Lee method is used to determine the incident energy for locations with voltage greater than 15 kV, which is obviously going to give you unrealistic incident energy. The voltage of the equipment plays a key role that the actual arc flash incident energy is based on the system nominal voltage instead of actually using the voltage across the arc. The arc fault method, the incident energy was very close to 41.216 calories per centimeter square. And this basically would also give us the upstream protective device using our trace tool which we were able to find out that that's the only protective device that could clear the fault in this particular condition. The time current curve for this particular condition would show that on a fault at that 34.5 kV switchgear substation, in this case, we do have the clearing time at this particular location, which was actually evaluated based on their existing settings for their time or current position. The instantaneous revised edition, where they had the same relay having two different settings under two different conditions, basically. So the first condition was the OC level 1, that we had the overcurrent relay with the instantaneous enabled with a six cycle delay, and then the OC2 level, where with a 0 cycle instantaneous delay was used by the particular condition for this particular application only for arc flash results. So these two multi-function outputs from the same relay was one for used for the short circuit coordination to avoid any potential selectivity issues. However, for arc flash, using the instantaneous setting gave us the correct expected incident energy to be way less than the actual calculated value. So in this case, we did have the PV arrays on, which seemed to be the worst case, where all the contribution of the sources were included. And we had our remarks on our wizard that we could use the maintenance mode as a maintenance mode setting, which is none other than the instantaneous enabled, where we were able to bring it down to 5.725 calories per centimeter square, which turned out to be the same location, which was very higher in terms of the final incident energy calculation. So the overall summary was tabulated in this results for illustration, where we did have the Lee method, which was originally given to us, which would give us a very high incident energy. And based on the arc fault EPRI method, we were able to get closer to a incident energy that could be accommodated with the available PPE. And once we submitted our findings, the actual substation client was able to give us another instantaneous setting enabled exclusively for arc flash to reduce the incident energy levels. And for each particular level, we had an arc flash label, and that was used to be given to the client as the worst case arc flash incident energy for the entire facility. The tail end to this particular application ended up on the DC arc flash side, which is on the PV array side of the actual the renewable sources that was added to this particular project, which actually had the voltages at this particular level, which would not be applicable for some of the methods that we already have in ETAP. So the choice of the right method for this particular application for 1100 volts DC was chosen to be the Stokes and Oppenlander. And so the scope of the study had PV arrays that are actually connected to the inverter combiner box, and that combiner box would in turn give us the connection to the actual AC side of it that goes to the actual facility at the 34.5 kV switch gears. So in this case, we had two locations of interest. One was the recombiner box, which could basically calculate the incident energy at 2-second rule, assuming all the particular PV arrays were actually added to that particular, contributing to the fault as a worst case. So we had the all-on facility, and then we have one PV array for that particular PV only, where we would actually calculate the incident energy for the fuse disconnect. So we had two scenarios established, one for the evaluating the worst case inverter recombiner locations fed by all PV arrays for DC arc flash, and the second scenario for each PV disconnect where the disconnect fuse is locked out and tagged out respectively. So the biggest challenge was we did have the actual height, width, and depth of the particular fuse disconnect as well as the recombiner box. However, we were kind of focusing on the worst case incident energy that the Stokes method could give us in order to establish the correct gap between the conductors. So we were trying to come up with these numbers so that we choose the gap between the electrodes and conductors in such a way that it is not longer than the width of the enclosure, but at the same time, it's the right gap value that was selected in such a way that it is going to give us the highest and the worst conservative incident energy. To evaluate the same, we use the power calculator tool, and we use the calculator tool to evaluate on this particular condition to give us the corresponding gap between the conductors. So in this case, we use the iterative process using the time slider, and we start with the original gap, a typical gap of 25 millimeters, and we started increasing the gap in such a way that the incident energy at one point of time starts to a very maximum peak value and then starts to reduce basically. So that was happening at 121 millimeters, which was the highest incident energy that was given, and that was still not the size of the width of the enclosure or the width of the fuse disconnect, and it was still less than that. So we choose that as our best approximation to get that gap between the conductors, because we do not have any standards or documents or any references to get that accurate value, rather than just physically measuring the gap between the conductors on a running facility. So this was not given to us, so we were able to use the analysis tools from ETAP to best estimate the gap in such a way that the incident energy is not under conservative. So based on these two locations, we had the first recombiner box. We used the 2-second rule to determine the incident energy. And obviously, there was no condition here. We were able to get the values at 46 calories per centimeter square using the 2-second rule. And then for the PV disconnect, assuming that the disconnect fuse is locked and tagged out, we add the incident energy directly coming from the PV array to the disconnect location. And the highest incident energy was somewhere around 1.271 calories per centimeter square, because we have to rely on the 2-second rule, as there is no upstream protective device that is directly fit from the PV array to the disconnects box, actually, the fuse disconnect box. Based on these results, the arc flash labels were printed for both the recombiner box and the worst case location at the fuse disconnect, and that was also added to our final report basically. Based on all these analysis performed and the lessons learned in terms of determining the right gap between the conductors, choosing the right mitigation technique, and choosing the appropriate method, the following conclusions were derived. The first one is we make sure that the equipment modeling and the arc flash input parameters can have a significant impact on the analysis results. So the main concern is choosing the correct switchgear type and the corresponding input parameters that included the actual dimensions, gap between the conductors, electrode configurations, make a significant impact on the analysis results. And then the choice of the appropriate methodology for incident energy analysis is important based on the application. The good example that we learned here was on the 34.5 kV side, where the 1584 method or the Lee method cannot be used due to high unrealistic results, which shift our gears to the arc fault method that ETAP has with system study capability, same as other studies, and we are able to get the incident energy within the appropriate limits. The third one is the what if scenario tools to recommend settings for incident energy mitigation or selecting input parameters is useful with ETAP power calculator tool. So the what if scenario refers to, okay, now that the fuse cannot be changed on the 34.5 kV side because it's already been installed, the only other mitigation technique is to basically use the working distance, or probably increase the working distance. But doing it every time as to choose the correct working distance, that is not going to give you under conservative results, but at the same time not going to exceed the 40 cal suit, would be definitely considered by using the power calculator tool or the plots option that was used in the arc flash calculator, which minimized and reduced a lot of man hours, and it helped us to finish the project on time. And on top of that, selecting the gap between the conductors on a DC equipment where the equipment access or measurements are not possible, the Stokes and Oppenlander method was used to estimate the gap between the conductors for this particular location where the maximum power method cannot be used. With that, I would like to pause at the moment and open for any questions or feedback or comments. And I thank you once again for attending this presentation, and we look forward to hear you with your feedback and comments on this particular case. Thank you. Have a good day.